Hi everyone, this is Becky, and in this video we are going to take a closer look at redox reactions. So the goals of this video are for you to be able to identify a reaction occurring as a redox reaction, to be able to assign oxidation states or oxidation numbers to elements and compounds and ions, and then to use the changes in oxidation states to be able to identify what is being oxidized and what is being reduced in a redox reaction. When we talk about types of reactions, right, we talked about these 5 different types where we have double exchange and then single replacement, synthesis, decomposition, and combustion. Really, we can separate these 5 different types of reactions into 2 broader categories, where we have the double exchange reactions, which just involve ions changing partners. And we've talked about these extensively in class. And then we have these other guys over here, where we're looking at synthesis, decomposition, combustion, and single replacement. These guys over here all involve electron transfer. In double exchange reactions, only the ions are changing. The electrons aren't, because the charges on the ions never change. But in these reactions, in the synthesis, in these set, electrons are changing hands. Electrons are transferring. And any reaction that involves electron transfer are redox reactions. So all of these, single replacement, the synthesis, decomposition, and combustion, are part of a larger category called redox. Okay, and so redox is an abbreviation for oxidation reduction. And in oxidation reduction, we have some species that is gaining electrons. If it's gaining electrons, it is being reduced. And if it's losing electrons, it's being oxidized. Right, so things that lose electrons are oxidized, things that are gaining electrons are reduced. To help you remember that, we have a couple of mnemonics. One of them is oil rake, where oxidation is loss, reduction is gain. The other way to remember this is with Leo, the lion goes grr, where losing electrons is oxidation, gaining electrons reduction. Doesn't matter which one of those you prefer. Both of those will help you remember that if losing electrons, it's being oxidized, gaining electrons is being reduced. So if we take a look at this reaction that we have down here, where we're reacting sodium metal with chloride gas to get sodium chloride salt. Okay, so in this reaction, what's happening, really, when I break this down, is I have sodium metal. So sodium metal is turning into sodium ion. All right, because it's sodium metal over here, sodium ion over here. In order to do that, and I'm just going to put 2's here because of the balanced equation here, I have to take electrons away from it. Right, so the sodium metal is losing electrons to go from Na to Na+, and the chlorine is gaining electrons to go to Cl-. So in this case, right, the sodium is losing electrons, so it is being oxidized. And the chlorine is gaining electrons, so it is being reduced, right? So a couple of things to keep in mind about oxidation, about redox reactions and oxidation and reduction in general. Number one, they have to happen together. Something can't be oxidized without something else also being reduced, because electrons can't just disappear or appear from nowhere. So, and in this case, when we're looking at just this particular reaction or reactions like this, it's somewhat easy to determine what's being oxidized and reduced because we're directly forming ions. Sometimes we're not, right? Sometimes we're forming things that have shared electrons, or we're looking at that, which means that we need a way to be able to track electrons in order for us to determine whether or not a particular reaction is redox. So the way that we do that is by assigning something called an oxidation state or an oxidation number to all elements that are present in a compound or in a reaction. Oxidation states are an arbitrary way of assigning shared electrons to elements. So basically what we're doing is we're taking these shared electrons and arbitrarily but consistently assigning them to particular atoms in compounds, which allows us to track electrons. Couple of things. Number one, and really, really important, an oxidation state is not a charge. This is just an arbitrary number. This really doesn't tell us anything about the element. It's not a charge. It just is a way for us to arbitrarily but consistently track electrons. And in fact, when we write oxidation states, right, so let's say that I have aluminum with a 3+ charge. Remember, charges, we always write as the number then the sign. For oxidation states, it's actually going to be backwards. So if I'm writing an oxidation state, it's going to be the sign then the number. So if something has a charge of 3 plus, it will have an oxidation state of +3. Right, so this is just a way to keep consistent in terms of notation. So how do we do this, right? If we're going to do this, how do we assign these arbitrary numbers? So we have a couple of rules to help us with tracking these electrons and with assigning oxidation states. The first one is that if I have an element that is by itself, it has an oxidation state of 0. So for example, if I just have O2, its oxidation state is 0, like aluminum, also oxidation state is 0. Anytime you have an element by itself, it's 0. If I have an ion with a charge, like a monatomic ion, so like for example, aluminum ion, so aluminum with a 3 plus charge, its oxidation state is going to be equal to the charge on the ion. So aluminum with a 3 plus charge has an oxidation state of +3. If I have F with a -1 charge, its oxidation state is fluorine with a -1 charge, its oxidation state is -1. Okay, hydrogen is always going to be +1 when it's with a nonmetal. It can be -1 when it's with a metal, but when it's with a nonmetal, it's going to be +1. So for example, if I have NH3, in NH3, the hydrogen has an oxidation state of +1. Oxygen is always going to be -2 unless it's with a peroxide. And if it's in a peroxide, it's going to be -1. And then when it's bonded to fluorine, because of rule number 6, it's going to actually have a positive oxidation state, but those conditions are pretty rare. So for example, if I have SO2, right, in SO2, oxygen is going to be -2. In H2O, oxygen is -2, hydrogen is +1. Okay, which leads us to the next rule, which is that if the sum of the oxidation states, so if I have something that has multi-atom, more than one atom, whether it be a polyatomic ion or a compound, the sum of the oxidation states has to add up to equal something special. It has to add up to be 0 if the compound is neutral, and if it has to add up to be the charge if the compound is a polyatomic ion. So for example, if I have H2CO3, right, the sum of the oxidation states here has to add up to be 0. I know the oxygen is going to be -2, hydrogen is going to be +1, so that's -2 times 3, so that's -6 plus 4 from the hydrogen, which means that carbon has to be +2, sorry, because I can't do math. Right, so the hydrogen is +1, the carbon is +4, and the oxygen is -2. If we look at this guy, so SO2, right, if the oxygen is -2, that sulfur has to be +4 in terms of oxidation states for the sum to be 0. Right, if the charge is, if it has to be the charge on a polyatomic ion, if I have something like SO4 with a 2- charge, if the oxygen is -2, and there's 4 of them, that gives us a total of -8 in terms of oxidation states, which means the sulfur has to be +6, so that the overall oxidation state, the sum of the oxidation states is equal to the charge on the ion. Okay, if all else fails, if you can't get there using any, like if none of these rules seem to apply, if you have the most electronegative element in your compound, you're going to assign it an oxidation state that's equal to its charge as a negative ion. So for example, if I have SF6, right, SF6 sulfur doesn't have any oxygen, doesn't have any hydrogen, the sum is going to be 0, but I don't know what either one is yet, so I can't use that rule. In that case, the fluorine is more electronegative than the sulfur, so we're going to assign that an oxidation state of -1, which means the sulfur is assigned an oxidation state of +6. Okay? All right, so given all of that, take a look at these. Pause the video, assign oxidation states to all of the elements, and then hit play when you're ready to see the answers. Okay, so let's take a look at these. If I have NO3 minus, remember oxygen when it's in a compound is going to be -2. That's -6. The total overall oxidation state has to be -1, which means the nitrogen is +5. Hydrogen is +1, which means the sulfur has to be -2. Right? This is an ionic compound here. Oxygen is going to be -2 because it has a charge of 2-, and the sodium is going to be +1 because it has a charge of 1+. And then in this one, H2SO4, oxygen is going to be -2, hydrogen is going to be +1, and the sulfur here is going to be +6 in order for those things to balance out and for the overall total oxidation state to add up to be 0. MgCl2 is an ionic compound, so the magnesium is +2 because it has a charge of 2+, and chlorine is 1- because it has is -1 because it has a charge of 1-. CO3 2-, oxygen is -2, so that's -6, which means the carbon has to be +4. Okay. All right, so now that we can assign oxidation states, what we need to do is track them throughout the course of a reaction. So let's say that I have this reaction where I'm reacting sodium with water to get hydrogen gas and sodium hydroxide. In order to determine what's being oxidized and what's being reduced, what I'm going to do is assign oxidation states and then use that to track electrons over the course of the reaction. So sodium is a metal by itself, so that's going to get an oxidation state of 0. Hydrogen's +1, oxygen's -2. Hydrogen over here on the product side is 0. Sodium is +1, oxygen is -2, hydrogen is +1. So if we look at this reaction, I have the sodium, which is, look at what's changing. The sodium is going from a 0 oxidation state to +1. And some of the hydrogen is going from +1 to 0, right? So the sodium oxidation state is getting more positive, which means it's being oxidized, because we're losing electrons, right? And the hydrogen oxidation state is getting less positive and more negative. So it is being reduced, right? So in this reaction, we're oxidizing the sodium and reducing the hydrogen, okay? Let's take a look at another example. So in this case, I'm taking copper chloride and reacting it with aluminum. So the copper is +2 in this case, because it's got a 2+ charge. This is -1. This is going to be 0. This is +3. This is -1. And this is 0. So if I'm looking at the things that are changing are going to be copper and aluminum. So aluminum is going from 0 to 3+ to +3. And copper is going from +2 to 0, right? So aluminum's oxidation state is getting more positive, so it's being oxidized. Copper's oxidation state is getting more negative, so it's being reduced. All right? Let's give one a try. So try this one. Pause the video. What I want you to do is balance this equation for the smelting of copper, assign oxidation states to all species, and then identify what's being oxidized and what's being reduced. Hit play when you're ready to see the answer. Okay, so let's take a look at this. To balance our equation, the oxygens aren't balanced, so I end up needing a 2 in front of that and a 2 in front of the Cu over there to balance out the oxygens and balance out everything else. Okay, so in terms of oxidation states, copper here has a 2+ charge, so it's going to be +2. Oxygen is -2. Carbon is 0. This copper here over here is 0, element by itself. This is +4. This is -2. Okay. So in terms of what's being oxidized and what's being reduced, we have copper that's going from a +2 to 0, which means it is being reduced because it's gaining electrons, right? The oxidation state is getting more negative. And carbon is going from 0 to +4. It is losing electrons, so it is being oxidized. All right, so there's more practice problems with this in your packet, but I'd like to leave you with the following challenge. So please, you must attempt this to get full credit on your homework, but I have magnesium metal and I'm adding it to a solution of hydrochloric acid. What I want you to do is I want you to write the balanced equation for the reaction that occurs, including states, states of matter. Then I want you to write the net ionic equation for the reaction that's happening. So write out the complete ionic, figure out what's changing and what's not, and then assign oxidation states to all species. You can do this from the balanced equation, or you can do this from the net ionic, and then identify what's being oxidized and what is being reduced, okay? Give that a shot. Bring it with you to class next time we meet. We'll see you then. Thanks.